there is a problem on the practice exam, question number 3, that looks like a conservation of momentum problem. And I think it'd be a good one to know how to solve. So let me show you how to do that here. So here's what the problem says. You get these two astronauts, they're in space, and they're touching each other, they're connected, and one is 60 kilograms, and the other one is 80 kilograms. But then they push each other apart, and so one goes off to be 12 meters away in a certain amount of time. They don't tell you what the time is. And the other one goes off to be some other distance. We don't know what that is. And our job is to figure out what this distance x is. So a good way to think about this is that it's probably just conservation of momentum. If we can understand the momentum that they had at the very beginning, whatever this momentum was, so I'll call that P initial, that's got to equal the momentum here, P final. So if I can set these guys equal to each other, then I have some way of solving the problem. And remember that momentum is basically going to be some sort of mass times some sort of velocity. And I'm going to get into that in the next page here. All right, so here we go. Let's do this. Go to black. All right, so right here, let's look at the initial momentum. So the initial momentum is going to be the mass of the first astronaut, let's say ma, plus the initial velocity of that astronaut, plus the mass of astronaut B times the velocity of astronaut B. So this is the initial momentum. The final momentum is going to be the mass of astronaut A times the velocity of astronaut A prime, okay? So this is after they pushed each other, plus the mass of astronaut B times the velocity of astronaut B prime, like that. And I'll just use the prime to distinguish between after the push and before the push. So the first case is kind of easy. They're both just sitting here. They're sitting here like that, and they actually have no velocity at all. So if I want to be honest about this, this velocity is 0 and this velocity is 0. So the initial momentum is just equal to 0. And because the initial momentum must equal the final momentum, what I can say here is that then this equation here, the mass of astronaut A times velocity of astronaut A plus mass of astronaut B times velocity of astronaut B, all that has to equal 0. Well, that's convenient because then I can put one of these things on the other side. So I can basically subtract from both sides the mass of B times velocity of B, okay? And so now I get mass of astronaut A times velocity of astronaut A equals the negative of mass of astronaut B times velocity of astronaut B after the push. So I have something like that. Okay, so let's go a little bit further with this. I can put in the values of these astronauts because I know their masses, all right? So this one's 60 kilograms, so that's astronaut A. Velocity of A prime equals minus 80 kilograms. That's what we were told for astronaut B, V prime, like this. Now, I don't know the velocity of astronaut A. So remember, this is astronaut A and this is astronaut B here. I don't know the velocity of astronaut A, but I do know that in a certain amount of time, he traveled 12 meters. So 12 meters. So what I could do is I could just say in 1 second, 12 meters. So I'm just going to hypothesize that it takes 1 second. So what that means is the velocity of A is going to be 12 meters per second. Let's just say that. Now, if I get that velocity, then let's see if I can get the velocity of astronaut B from that. All right, so now let's continue, plug in the equation, and see what we get. So I got 60 kilograms, that's astronaut A. Velocity of A is 12 meters per second equals minus 80 kilograms times velocity of B. Okay, so I'm going to divide 60 kilograms divided by minus 80 kilograms, 12 meters per second, equals velocity B, like that. And now I can do a lot of simplification. So I can cancel the zeros out, and 6 over 8 is really like 3 over 4. And this is 12 meters per second, like that. And I've got a 4 here, and I got 3 4s there. So this is going to end up being 3 meters times 3 per second, 9 meters per second. So the velocity of B is 9 meters per second. So in 1 second, which is how much time we allowed astronaut A to travel, in 1 second, astronaut A traveled 12 meters. So in 1 second, how far would astronaut B? Astronaut B would travel basically 9 meters per second. This is trivial, times 1 second. It's going to equal 9 meters. So 9 meters is the distance that astronaut B would have traveled. So we can go over here and erase that and put in 9 meters. And that should make sense, because if we've got conservation of momentum, remember that if I have a smaller mass here, so astronaut A is 60 kilograms, that'll have a bigger velocity. And here, astronaut B has a larger mass, so they're going to have a smaller velocity, somewhat smaller. So they travel somewhat less distance in the time that they go compared to the distance traveled by astronaut A. Hopefully this is helpful. Again, let me know if you got questions or comments. Thanks.